All right, there's a few more people coming in, but I'm going to get started because this talk fills half an hour. Alex, thank you. All right, so yeah, I put this abstract in, and it was originally called Handling Complex Guest Exits with eBPF, which sounds really grand, and maybe that's why I got accepted. But in reality, I only did MMIO. So if you're interested in other types of complex guest exits, this isn't for you. Before I jump in, who am I? That's what I look like when I'm smiling. I'm an upstream kernel hacker. I'm 64 architecture co-maintainer with Catalin Marinus. That's the core architecture, not the KVM bits. I'm employed by Google in the Android systems team, mainly working on PKVM, which we spoke to you lot to death about at the last KVM forum. And I'd rather be fishing or brewing beer. So before I jump in, I feel like I need to give a disclaimer because I really don't know anything about eBPF. Does anyone here know about the internals of eBPF? Maybe Alex, someone at the back. Great, I might need your help afterwards. Okay. Yeah, I've definitely got, there's plenty, like, this was kind of an excuse to play with it, but I definitely have more questions when I started. It's a work in progress, it's all a moving target. I'm not even convinced it's a sensible idea, but I'm hoping to plant a few seeds. I do think it's cool. I did fix a code gen bug in the verifier, so at least something good came out of this work. And it was very much confidence-driven development. When I put in the abstract, I had no code, didn't really know if this would work, and then it got accepted, so I was kind of, need to make something work. So I got a prototype, which I'm going to try and demo if I have enough time. So you should all be familiar probably with the basic model for I/O handling in KVM. This is an MMIO type thing, or virtio in this case. So I'll just whiz through this to sort of set the scene. So the application does some sort of write, goes into the guest kernel, chucks some data into the vring, which is a piece of shared memory for the virtio device. At some point, we're going to trap because we're going to ring a doorbell, and that's that write L at the bottom. That goes out, routed through the hypervisor, and on ARM64, we go back into the host kernel via this IO member abort path, which in the traditional model then goes back to the VMM and user space with this KVM exit MMIO reason. And then QEMU here can figure out what it wants to do with that. It can go and look at the queue, it can process those descriptors, and probably issue system calls back into the host kernel. So it's a bit silly because you kind of go out just to come back in again on the host side, which, you know, it's performance, it's latency. So for some devices, you can do better. You can keep that handling in the host kernel using this thing called vhost. So now you can see, I mean, QEMU still had to do some work here. It still knows about the device. It's had to do some IOC tools to set it up. But once it's up and running in the steady state, you kind of just stay in the host kernel handling those exits. And that's faster, and that's widely used, right? But it does have some limitations. It does result in thousands of lines of device-specific C code running in the host kernel with elevated privilege because it's in the host kernel. It doesn't really need the privilege. It's just we don't want to go out to come back in again. But it's not brilliant. It only supports virtio. If you want to use other device emulation in the kernel, then you have to use this KVM create device IOC tool, which I'll talk about later. But that's then all device-specific interfaces. The VMM still needs built-in knowledge of the device because it needs to be able to drive the vhost configuration, for example. And it's hard or impossible in some cases to update these at runtime. You need to reboot the whole host to update your device, which is obviously painful. You've got to migrate guests off. And like I said, it's privileged code running. It cannot be sandboxed. So after a few beers in the pub, I was like, you know what? Maybe this is a paraphrase of me, I think. Maybe we should use eBPF to handle guest exits. Oh, cheers. Yeah, right. Well, actually, I thought about it the next day, and maybe we could, right? Let's give it a go. I need something for KVM Forum, and it was only September. I haven't really done much since then, so let's put this in. So can eBPF save the day? So eBPF, for those who don't know, is a bytecode language originating from the networking side. I think it's Berkeley Packet Filter, and then they extended it. I think it's extended. Yes, extended Berkeley Packet Filter. So this is a bytecode where you can upload programs into the host kernel and attach them to certain parts of the kernel, and they can then run in response to different things, like receiving a packet, for example. And it's quite cool because when you load those bytecode programs into the kernel, they go through a verifier, and this verifier will check, for example, that you're not going out of bounds of an array and trying to access kernel data structures. It'll also try to check that you have bounded loops, which probably isn't possible in a general case, but it will reject programs that it doesn't like the look of. It's quite flexible, so there's an API from userspace, which is then portable, so in theory you can upload these programs regardless of the architecture, and the kernel will JIT them to the underlying machine code. And there's also an interface to the BPF programs themselves. So a BPF program can call certain functions within the kernel. So it kind of has its own sort of system call interface, but they're not system calls, they're just function calls. And they're called BPF helper functions that you can invoke. It's pretty fashionable, which is really good for conference submissions, as I'm proving. On the downside, like what I'm trying to do is quite atypical. Handling guest exits for MMIO is not really the kind of thing. I think it's pushing at the edge of what you might want to do with eBPF. The permissions model in particular is very rigid. You know, you have these helper functions you can call, and if you have no privilege, you can call this bucket of helper functions. And if you have a bit more privilege, you can also call all of these other functions. And if you're root, you can call even more functions. But it feels a bit, you can't say, I just want this helper, or I want this helper but only with these FDs, or you don't have that kind of fine-grained thing that you have with system calls. And it's fashionable, which is also bad because it's moving really quickly. So what have I done? So I did some hacking, and I came up with this new kernel, in-kernel device, which is KVM dev type BPF, and I'm going to just explain a bit about how that works. So I've modified the previous diagram. I haven't managed to get virtio working, so this is just a really boring MMIO access, but let's just say we've got an MMIO exit. We're going back into IMM abort down the bottom into the host kernel. What happens in this model is instead of dispatching to the vhost driver, we dispatch to a program in the eBPF JIT, which has been attached by QEMU. And effectively, that allows the BPF program to handle the MMIO exit. And so we should get all the benefits of vhost in terms of latency and performance, but hopefully none of the downsides, because you can upload this stuff at runtime, it's sandboxed, you can update it, the VMM might not need to know very much about what's going on, which is quite scary. So here's the programming interface from the VMM side. So the dev type BPF is a new device type, and you instantiate one of these in the prototype I have with this KVM create device IOC tool, and then you can set attributes on that device. And the main one you can set is you can actually set an MMIO range where you want these programs to run. So that's the struct you pass from userspace. The address there is a guest physical address. So you can say, you know, a guest physical address blah, I want however many pages of MMIO space, and when the guest does an MMIO read on that region, I want you to run the program specified by readFD, and if it does a write, I want you to run the program specified by the writeFD. And those FDs are file handles that you get back from the BPF system call after you've successfully loaded your bytecode programs. So it's kind of two steps. You load your programs first, then you attach them to MMIO space. libbpf makes that really easy. It's just like as a function you call to go, hey, just go and load this for me. And if the verifier is happy, you get your FDs. I think you can do a similar interface for virtual interrupts. I'm like halfway through implementing that, and I ran out of time. I had to do the slides. But I think you can attach virtual interrupts and then signal them as well from BPF. So that's the VMM view to BPF. The other side of the sort of interface is what the BPF program itself sees. So when you attach your read program, for example, and you get invoked in response to an MMIO read, you get a single pointer, which is a pointer to the context. So this is the structure I've come up with. This is quite interesting for a bunch of reasons. I'll just walk through the fields, and then I'll talk about why it's interesting. So we've got a 64-bit or 8-byte buffer. That's the transfer buffer. So either it's, you're either reading the data there or writing it, depending on the direction of the MMIO. You've got an offset within the region, which is the offset that is being accessed. So you might be like a certain device register, for example. The length of the access and padding, and then the vCPU ID. I'll talk about why we need that later. But the interesting thing about this struct is it's completely fake. It's never allocated. And this is kind of one of the flexibilities of BPF that is quite powerful, I think. When you access fields in this struct, the JIT will JIT accesses to actual internal kernel data structures. So if I read vCPU ID here, I'm going to JIT an access into the struct vCPU and pull out the ID, but without exposing struct vCPU in the kernel user API, which I think is quite cool. So this is like your interface to the underlying data. And it also means that you can do things like, for example, if you're in the MMIO write handler, I can make the buffer read only, and I can refuse to load a program that tries to write to the buffer. So you get sort of fine-grained permissions on what these programs can and can't do. So your program runs. If it returns 0, handled, skip the faulting instruction, back to the guest. If you return non-zero, we're going to go back to the VMM. Maybe we couldn't handle it for whatever reason. So that's cool. What? How do you sort of package this up? So I've tried to come up with this concept of having a device as an ELF file, which is quite interesting. It's not the normal way that you ship BPF programs or distribute BPF programs. And basically, I take you get an object file. I'll show you this in a minute with your read and write functions, and then I add this note that I've come up with. It's just some formatted note, an ELF note, which describes properties of the device. For example, how much MMIO space it needs, what its device tree compatible string is, or what its ACPI description is. And you can, in theory, then get to a point where the VMM doesn't need to know anything about the device. It can parse the note to figure out how to tell the guest about it, attach these programs, and you're away with a mixer. Linkers really hate this, so I had to use optcopy, but you'll see that. Linkers just segfault when I tried to link this thing. So this is what I just described. Probably should have skipped ahead to this. So you've got your functions on the left-hand side, along with a note. You compile that with LLVM. So you don't have to write this in bytecode. You can write it in C, or if you're cool, you can write it in Rust. You then partially link that to get your relocatable ELF file, which you can feed to the VMM. In this case, I'm using KVM tool. That will have instantiated this dev type BPF. We can attach the programs to it. And now when the VM takes an MMIO exit, it's handled in the sandbox, and it can call into these helpers. So that's kind of how it works. Shall we try and do a live demo? So this is probably not going to work, but let's see. Can everybody see that? Okay, thank you. So this is just on an ARM64 hacker, so this is an AR64 environment, but it's just running in QEMU TCG on my laptop, so it's really slow. It's really, really slow. So you can see this is my hacked up 6.3 kernel with all that stuff in that I was talking about. So what shall I show you first? If we go into this BPF devices directory, this is a standalone directory where I've got two devices. The one I'll talk about is the PLO31. That's an ARM real-time clock, right? It's a simple device, but that's the one I've just had a crack at emulating some of it. So let's just have a quick look at that. I'll show you roughly how this works. So, okay, boring stuff at the top. We've got some register definitions. You can just get that from the technical reference manual. And this is C code. Here's the structure I was on about earlier on. The fake structure, it's missing the vCPU ID because I don't need it here, but it doesn't matter because it's never allocated. So the first thing that's interesting is this maps section. So this map section is, this is what you use to have, basically have global state. So you create here a BPF map. So a map is, you can have things like hash tables with maps. You can have things like arrays per CPU data structures, whatever. I'm just using an array here, a 4-entry array of U32s. That acts as the persistent device state. So the read program and the write program can mutate the maps, and it will persist after the programs have finished. So that's what you can sort of use to just have the internal device state. And I've just got 4 because there's some 4 registers. Then I have these helpers for reading and writing those registers. So you can call, here's invoking a BPF helper, BPF map lookup LM, right? So that's how you index into the map. So that's for reading a register, that's for writing a register. I've got some funny stuff here for calculating some time. Look, some more BPF helpers here for getting the International Atomic Time, for example, because it's an RTC. I want to find out what the time is. Here is a read program. So this is all macro soup, but hopefully you can see we have a read program. It takes in the context pointer. We extract the offset. We switch on the offset. And depending on which register you're accessing, I either just read it out of our shared state, or I calculate what the value should be based on the international time, or I just return some hard-coded values because there's some ID registers at the end. So it's very simple. You can see there I'm just setting the buffer to be whatever the ID byte should be. And at the end, we'll either return 0 because we liked it, or ENXIO if it was a register that we don't implement. And the write program is similar. So we can build this, ignore the optcopy invocation that's going to fly past eventually. Yeah, that's horrible, ignore that. Get rid of it. Right, now what I can show you, if we look in here. Okay, so we've got our ELF file, and you can see, hey, it's eBPF. We can look at the sections of this thing. You can see our note. Oh, I'll show you the source code for the note as well, because that's a little bit interesting. There's a whole bunch of different things. And here are our read and write programs. You have to put them in their own section, because libBPF wants them like that. Yeah, sorry, I meant to show you the note. Let's have a look at the note. So the note is, I mean, this is just, if you've ever looked at creating ELF notes by hand, it's fairly painful. But for example, here I'm saying the compatible string of the device is ARM prime cell, so that the VMM can create a DT node from it. What else can we do with this? We can probably obj dump it, if you want to have a look, in case you don't believe me. Device.o. Okay, this is what BPF disassembly looks like. So here's the read devreg function. It'd be nice if it was sort of formatted better, but you can see here's the call to that function that does the lookup, right? Oops, watch out for that. Okay, so I'm going to boot a guest first. So first of all, I'm just going to boot a normal KVM tool guest. Remember, this is in TCG, so it's pretty bad. And you can see this is without the RTC, so we're stuck in 1970, which is probably better for music, but not a lot else. So let's get out of 1970. And now what I can do is, if I pass, you can see now, sorry, can everyone see that? Is it too low down? I don't really know how to make it go higher up, but I'm passing minus BPF, and then I'm passing it the L file that I was obj dumping earlier on, right? So all I'm saying to KVM tool is use this. KVM tool has no knowledge about RTCs at all. It's just going to take in this device, it's going to parse that note, generate the correct DT entry, and then attach the programs. So now, hopefully, if we scroll up, you can see, I'll leave it at the top, you can see sort of here that it's found the PLO31, this is our emulation, and it's set the clock, and it's not 1970 anymore. So that's cool, it's working, right? Sorry, this is going to be at the bottom. I don't really have a way of fixing that. I guess I can hit enter a few times after each command. Control L. Yeah, didn't work. Okay, so there we go, put it up. So you can see I ran HW clock minus I. You can interrogate the clock like that. What else is interesting? Yeah, I know what we can do. So if we switch back to the host, so this is a root shell on the host. BPF has lots of tools associated with it, so you can do things like BPF tool prog show on the host, and you can see our IO read and our IO write functions are loaded into the JIT, right? And there's lots of information about how big the program is, and the BTF IDs, and when we loaded it, and what the UID is, and that kind of stuff. There's a map ID of 1. So we can dump the maps. So here is that PLO31 reg map. That's our array, right? You can see it's 4 entries. So that's what's keeping the state. And you can then do things like, the syntax for this tool is horrible. I will make a mistake at some point. So you can dump it, right? So this is quite cool. We're now introspecting the state of the device. Actually, all the guest kernel has done at the moment is enable it. So there's like a 1 in the control register. The rest of it hasn't been touched. And you can even do things like serialize it into JSON. So maybe you could migrate the device if you were feeling brave. I don't think you can import this, but there's no reason you couldn't have a way of importing the internal state, right? If you wanted to migrate a device emulation. What else? Oh yeah, so there's a thing you can do. You can actually manipulate the map as well. So if we dump it again, now the syntax for this is really complicated, so just give me a minute. I think it is. You have to pass a key, which is the index, but for some reason you have to pass this as a series of bytes in big endian. I don't know why. Probably because it's from the networking people and it's faster. Something like that. Okay, so I just updated the value of index 0 to be 1. So now if I go back to my guest, which is still running. Okay, way, the music's good again. We're back in 1970. And then you can also set it again from here, I think. If we want to go home because we're sick of work and it's time to go to the pub, then you can set the clock to 5:30. And we should be back in the current time. Yeah, it's time to go to the pub. And if I dump the thing here, you can see now that lots of different register states been changed because there's 2 different registers that are programmed by the driver. So that's like the demo I have. Let's go back to the code, not the code, the slides. How long have I got? 10 minutes. All right, let's run through this. So one of the other motivations for this was some scheduler work from Sarah Vanner and David, who can't be here, but they're in my team at Google. And they helped me put this together, so I just wanted to give credit to them for that. So the problem, you'll see how this ties in a minute, just bear with me. There's a problem which Sarah Vanner has discussed, and there's stuff on the list, and it was discussed at Linux Plumbers. You can go and have a look at his slides. I just stole this from there. But what we see on Android is we get pretty bad performance when you have asymmetric big little systems, so CPUs in an SoC of different performance points and power points, and we have dynamic frequency scaling. And the guest doesn't know anything about this, so you get things like this, where you have a CPU-heavy workload, and on the host, if you run it, it starts off on CPU 0, so this purple box here is just the thread running, in case you're not familiar with these, and here's the frequency underneath. So you can see, hopefully I'm not too much in the way, but you start off on the small core, and it's CPU-intensive workload, and the frequency gets ramped up. And at some point, you run out of frequency, right? You can't make that small core any faster, so the scheduler says, well, okay, well, we're going to have to do it. So it shifts you over to the big core, and then you see the frequency ramping. And the whole thing, after 181 milliseconds, you're Fmax on the big CPU, right? Great. We kind of did a good job as the scheduler. But if you're in the same workload in a VM, we never get off the little core, just because the guest has no concept of that topology and no way of communicating to the host what it needs. So we get quite bad performance from that. Keep walking into this. So there's more information about it. You can have a look at the series on the list. The way that they proposed solving this, Sarah Vanner and David, was to add a new CPU frequency driver in the guest, which makes sense. The VMM pins the vCPUs, okay, let's just assume that happens. The guest CPU freak driver can then expose some of the host CPU properties, like this, what's it called, the capacity, the frequencies that are available, and then it can issue requests which correspond to uClamp utilization values. That's a way of communicating your utilization using shared set atta, the system call. But how do you communicate that? Well, initially I think they wanted to use hypercalls. Hypercalls are quite inflexible. It's an ABI for the hypervisor. Didn't really want to do that. Could use an MMIO device. Well, if we go back all the way to the beginning of my talk, putting that MMIO device out in user space is going to give us some latency. And for this kind of workload, it's really critical that you minimize that latency. Not only because the guest is runnable, right? We want to get every cycle spent on his path is wasted, but it's a fast path. Like the scheduler accesses these registers all the time, I think on every context switch. And the state of the system can change during that processing. So to keep the information up to date is really crucial. So we could do it with eBPF. So I had a crack at that. I had to add some new helpers. In fact, I can show you the code. Like, basically, there's some getters to get information. These are just returning information that you can already get in sysfs. The last one sets the uClamp values, so that's a wrapper around shared set atta. I didn't want to expose shared set atta in its entirety because it's a bit of a multiplexing system call, and you can do things like change to a real-time policy, which feels like something you don't want a BPF program to be able to do. But I'll just show you the code, and I'll explain these very rough numbers. Where is it? Here it is. So it's really, really small, right? As well as the font. I know it's a bit of a small font, but the code is also small, I promise you. So there's a read function and a write function. You can basically get the current frequency, or you can set a frequency, and we do some maths, and then we call the uClamp. Right? It's not complicated. Oh, is this going to take me back to the beginning? Please don't take me back to the beginning. Thank you. So some very rough results. I think these are literally from yesterday, so take them with a grain of salt. But running FIO under PKVM, so in PKVM we're bouncing I/O. There's actually quite a lot of CPU involved. You can see, to get in user space, we get a performance uplift. So this is like 13% faster. That's 10% faster. And it's interesting, right? Because I'm not talking about like the cost of the accesses to the new thing I'm talking about, or the exits. I'm not talking about the actual I/O throughput in the guest. But we were seeing sort of 23% for this one. This is the best number, so I picked it. But the random writes are 23% over this 13, or this is 15% over that. So it looks pretty promising. These are pretty massive numbers. So I think that's cool. If you want to have a look at the code, I have plenty of hacks for you. I've got my host kernel changes, so that's all the stuff I spoke about earlier on with the new device type. I don't yet have virtual IRQs working. I'm going to be getting that. I've got new program types. I'm maybe supposed to use this thing called BPF struct ops, which there's an LWN article about it, and it like makes your head spin. But yeah, that's all there. I've got this eBPF devices repository, again on kernel.org, which has the two devices I've spoken about, the PLO31 and the vCPU freak, and the horrible build system to spit out those elves. The KVM tool, which I used for the demo, that's basically the code to drive libbpf. And then there's a guest kernel driver for the vCPU freak device, which is in Gerrit here if you want to have a look. So it's all out there, it's all open source. And I think you can actually go slightly off piece with this, so it's already a bit wacky, but I've got some really weird ideas which are quite scary, and I just wanted to throw them out there in the last few minutes. So I'm quite nervous about the ABI and security implications of some of these. I don't quite know how to do asynchronous behavior. You can't block in BPF, so at the same time, it does have support for things like timers, so there must be a callback mechanism. I just need to spend some time understanding that. There's a scary helper called BPF copy from user, which would mean in theory that these BPF programs can go and slurp memory. If they've got enough privilege, they can slurp memory out of the vCPU thread that maybe corresponds to data structures that are, VMM data structures that are outside of guest address space. I think we should probably not want, I don't think we want that, but you could have a BPF guest accessor. For example, it could even take a guest physical address, and we could JIT the translation, or code to do the translation. And you could say this device can only access these certain parts of guest address space. I think that's quite powerful. Maybe someone could try and do vhost. I have no idea if that's plausible, but it'd be cool if you made it work. I think we do need finer grained permissions, something like you have for seccomp for system calls. We probably need something for BPF helpers to be able to nail this down. PCI devices to get x86 working. Maybe using that JSON state for device migration. The crazy idea I had at the end, which might be going too far, is you could even have a device which just has like a firmware upload register, and then the guest could upload the ELF files for the devices itself. So then the VMM doesn't even need any device emulation, right? The guest provides the devices and the drivers. I think you have to fix the permissions problem before that is remotely feasible. But sounds pretty cool. And your idea here, right? So in the last minute, I think this is cool, but I'm really not precious about it. Like I said, this is conference-driven development. I'd love it if other folks could have a play, see where they can take it. We can turn it on its head, we can chuck it away. I just thought it was interesting to talk about, interesting to think about. It's surprisingly powerful, I think. The security story definitely needs figuring out for some of this. But yeah, if you're interested, the code's all there, get in touch with me. Have fun. Thank you. So there might be time for one question.
Cool.
I knew it would be Alex.
Of course it would be. Is it on? Hello, hello. Ooh, it works. So first off, disclaimer. I basically experimented with similar things without BPF, just basically as a prototype, just to see how it works. I don't know, like 10, 12 years ago, and gave a presentation on KVM from that, if in case you want to see that. The main conclusion from that was, is as long as you live in an open source environment and ecosystem, and you kind of want to have things available and hackable for everybody, and you make the interfaces small and simple enough, there's very little reason to do any of this, even any device simulation in the kernel, because either you go and modify your guest host interfaces to be exitless, which is what you actually want, or you need to run legacy things. And at that point, you either do a device model in the kernel, which doesn't really help because it's half the cost.
So what would you propose instead for?
So for this particular use case you have, for example, the scheduler, you would need to have, say, you probably have something already in the kernel that polls for the current frequency, because your host needs to reschedule and analyze things, and you just basically move that into a shared page and share that page, and basically you have.
Yeah, for the readers you could do that, but you still end up with device-specific code. That's the first thing, and the second thing, like for the set, I don't see like setting a uclamp value. You could. When do you get that picked up? Like, you need to, because you need to act on it quickly.
Sure, but I'm not convinced that the exit to user space is really a significant performance impact.
I mean, I had numbers,
for the
right?
writes.
Like, if we can have a look at the numbers.
For the writes, only
Okay.
for the ones where you say like I'm hitting a threshold, I really need to go and do something proactively here now. You can probably even be smarter on doing them.
I
Even
mean,
less.
it is, right? Like
This
you
is
can
including
see-
for reads. This includes reads. So if you make the reads exit free, and you make the writes be slightly smarter, you don't need to write on every single time, right? You can
Yep.
basically write only when you exceed certain thresholds to actually go and jump to a newer frequency or whatever
Yep.
you want to give as permission. I'm pretty sure you'll see very similar performance
Okay.
numbers, or even better, probably even better than the BPPF MIO one, because you're not exiting. So the main conclusion I had back then was, as soon as you exit, you lost.
Yeah, so if you,
Because
so when I
it's
talked about
synchronizing.
the helpers earlier on, right, you could, I said there's this like user access functions, right? So if we had guest memory access functions, you could do exactly what you're talking about. You could have a BPF device that has a shared page, and that's the only page it can access. And you could even do things in the verifier and say, for example, the device can never read the page, it can only write it, and it can only write
You're
these
still
fields.
exiting.
No,
But
no,
the
you
problem-
wouldn't necessarily be exiting for that.
You're exiting. Well, if you're exiting the guest to the host, right?
It depends when you decide to run the program, right? So if you get the asynchronous stuff working, you can have a callback, and you could say, you know, when the value changes in the host, then you
So
go and write it to
So
the
what
page.
I think would be super cool is if you could do something similar where say your firmware in the guest could inject a BPF program into Linux to basically do device emulation straight inside its own context, right? That would completely remove any exits. But as long as you still take the exit from EL1 into EL2 back into EL1, all that dance, you already spent most of your time context synchronizing.
All right, we're out of time. Thank you, Alex, for the question. And